Clemson ECE Integrated Systems Design 2 Spring 2022 Team Journeyman would like to present Genesis, a modular rover design.
Genesis is a modular rover built to be a 3-month proof of concept. A robust, cost-effective solution was generated with the idea that it could be customizable with plug-and-play modules and serve multiple purposes across multiple industries, anywhere from defense to public safety to even industrial use. Genesis was designed to run sensing data autonomously in order to reduce the human risk of entering any hazardous environments. In addition, communication features were added to the rover to allow it to function as a home base should the need arise that unique communication is needed.
For this project, we produced several different deliverables. We created 2 different movement systems, a track system and a rocker bogie system. We developed environmental sensing modules capable of detecting carbon monoxide, radiation, temperature, pressure, humidity, and electromagnetic fields. We integrated a LiDAR camera that is capable of RGB color, depth, and person detection. Our system has a speaker module to broadcast audio files, a ham radio hotspot module, as well as a user-friendly UI system to select modules and control movement. The rover runs on a 2-battery power system and is controlled via Wi-Fi communication through a web server.
For our rover design, everything from the LiDAR camera to the sensors to the drivetrain are connected back to the central Raspberry Pi Model 4B. The ham radio module is connected to a separate Raspberry Pi Zero. We chose the Raspberry Pi because it's a cost-effective solution that offers all the features we need to power all of our peripherals. We have multiple cores we can take advantage of to run multiple programs that we made, and we have enough memory to make sure that running the software in the background won't be an issue. The Raspberry Pi also features Wi-Fi and Bluetooth connectivity for internet connection, as well as Bluetooth peripherals in case we need to attach those as well.
The Genesis rover systems operate on Raspberry Pi 4B architecture, which acts as the brains for the project. All of the modules on Genesis, including the movement system, are controlled through the Raspberry Pi. The rover movement system is based around a track system for level ground movement and an interchangeable rocker buggy system for obstacle traversing. The rover as a whole is based around a plug-and-play wiring system, which allows for all of the modules and movement systems to be easily interchanged as needed, with the ability to add additional modules if needed. A 2-battery system was integrated into Genesis so that the movement system is separately powered from the sensor modules of the rover. The sensor modules are all run through the SPI and I2C buses of the Raspberry Pi, and the speaker module and LiDAR camera are integrated into the Pi using the 3.5mm jack and onboard USB ports respectively. In order to keep all of these hardware components cooled, a push-pull cooling system using a top and back-mounted fan was integrated, ensuring adequate cooling was achieved.
For our software design philosophy, we wanted to take the same approach as we did to our hardware. We wanted to make the software modular and use multiple threads to run multiple small programs rather than having all of the code in one large file. This makes debugging significantly easier and makes the code look a lot more cleaner and easier to clean up. The data coming from the LiDAR camera is accessed by using Pi RealSense. The data from the GUI, the user interface, is sent using the MQTT protocol, and the GUI can also communicate to the rover for movement controls using the MQTT protocol. One last word on the use of threading for our software. Our modular approach to software design comes in handy because we can easily add or take away modules of the software in the future, which would allow for easier upgradability should we either upgrade the camera or add additional sensors in the future.
For the overall design methodology, a modular approach was employed such that modules could be developed in parallel, also allowing for groups to work on multiple modules at one time. Headers on different sensor modules allow for future interchangeability of sensors as well as additional sensor plate designs.
Genesis was originally planned to be powered through one power source, but was later switched to a 2-battery system in order to prevent as much power loss as possible through stepping up and down the voltage. A 5-volt, 27,000 milliamp hour smart battery acts as a UPS or uninterrupted power supply for the Raspberry Pi 4B, the ham radio hotspots Raspberry Pi Zero, and the LiDAR camera. The drivetrain and cooling system for Genesis is powered by a 12-volt, 3,000 milliamp hour lithium-ion battery that is running through a buck boost converter in order to regulate our voltage, as well as step the voltage up for the rocker buggy system's 12-volt requirements and step down the voltage for the track system's 6-volt requirements.
The sensor data is collected on the rover and is sent wirelessly to the user interface. This allows the operator of the rover to control the rover from anywhere in the world. In order to get this to work, we are using Python to control the rover, MQTT protocol to send data between the rover and the user interface, Django for building the user interface, and OpenCV to process our image data. In the following video, you can see our rover tracking people using a depth camera. Our image processing allows the rover to send the images to an external computer for processing. Handling image processing this way allows the detectable object to be changed wirelessly by the operator. Secondly, the image processing will not slow down or affect the battery life of the rover.
Our system utilizes several different sensors to collect data. We are using the SparkFun MQ9B to detect carbon monoxide, the Radiation Watch Type 5 Pocket Geiger radiation sensor to detect radiation, the Adafruit BME280 to sense air temperature, pressure, humidity, and altitude, and lastly, a homemade plate-style electromagnetic sensor to detect EM fields. This is our user interface that is utilized to control the rover. There are buttons to toggle to different sensors as well as movement controls. As shown, this is a normal reading for a radiation sensor after stabilization. It gives us estimated counts per minute. We can see spike in counts as we put a radiation test card in front of the sensor. For a carbon monoxide sensor, a voltage is read in corresponding to the amount of carbon monoxide that is in the air. When we exhale on the sensor, you can see an increase in voltage. For our temperature sensor, we can see stable values, but they increase if we hold a hand out in front of the sensor. Our pressure, humidity, and altitude remain stable with our current environment. The readings from the electromagnetic sensor are sinusoidal in nature, and the amplitude increases with EM field interference.
For our drivetrain system methodology, we supported two drivetrain systems, one being flat ground and one being rough terrain environmental movement. Our out-of-the-box solution provided us with a track system for flat ground and indoor usage, whereas our design solution was based on the NASA's rocker bogie system and used for a more rugged suspension design. For our movement system, the rover moves forward, backwards, and left and right with a 0-degree turn radius. The rocker bogie suspension design, inspired by NASA's Curiosity rover, allows for more rugged terrain movement.
The Genesis rover has a unique ham radio hotspot feature that is employed. Using a UHF-VHF-based radio, this module allows the user to communicate via Wi-Fi to any DMR digital radio talk group in the world, so long as they have the proper licenses. These licenses are an amateur radio license, DMR mark registration, and if using Brandmeister servers to set up digital talk groups, Brandmeister self-care registration. The Pi-Star dashboard is what the user will see whenever the hotspot is set up on the DMR web. A display allows the user to know if they are transmitting, actively picking up chatter on the net, or waiting for chatter. In addition, logs of all call signs that have accessed the hotspot are listed under gateway activity, and all the times local call signs, such as the users, have accessed the hotspot are listed under RF activity.
At the end of this project, we were quite proud of our results. We have sensors that are capable of detecting the level of carbon monoxide, temperature, pressure, humidity, altitude, electromagnetic field, and presence of radiation. We have a DMR digital ham radio hotspot 2 different interchangeable suspension systems and a 0-degree turn radius on our track system.
Over the course of the project, the biggest challenge our team faced was team communication in early stages. Problems typically were not addressed until they were too late, and many lacked foresight when it came to their roles and hardware selection. These problems were further exacerbated by very long shipping times and limitations, particularly due to the COVID-19 pandemic. Even though hardware limitations are minor, there is slight server interfacing speed with the Raspberry Pi because we are using a third-party server to communicate for wireless communication. Lastly, being that the project was very ambitious and very complex, the time crunch of only 6 months for one semester really presented a lot of problems and challenges in terms of meeting all of our goals in a timely fashion. Having an additional 3 weeks to 1 month would allow us to have a much more polished final design, though we are happy with how it turned out in the end.
For the future directions of this project, refining the plug-and-play aspect of the design would further reinforce modularity. For structural stability, changing the Rover material from PLA to lightweight metals like aluminum on critical parts, as well as gaining a deeper engineering influence in the drivetrain systems, would help the structural integrity of the project. More advanced module integration as well as better DMR halt group availability would further align us with the goals and ambitions originally set out for this project. In conclusion, this project has been a successful proof of concept for our modularized Rover idea. We have effectively met the original desired scope and vision of this project. This platform can be further developed with even greater functionality given the modularity and plug-and-play aspects shown in the previous slides.